Good evening everyone. So welcome back to fifth lecture of electromagnetic waves. So essentially this lecture should be our probably our last lecture of this chapter, electromagnetic waves. As far we have discussed every details of electromagnetic waves. So let me just give you the brief recap what we have done till now in this course, and after that we will proceed for this class. I will discuss in this class the spectrum of electromagnetic waves, which I have already discussed little bit in the very first lecture. In this lecture we will discuss in details, and after that we will do some numerical problems regarding this topic. Okay. So in the first lecture we have discussed the Maxwell equation, right? Maxwell equations in differential form. Okay, and from those four Maxwell's equation we derived the condition for electromagnetic waves, and we obtained that there are electric field and magnetic field both are perpendicular to each other, and also electric field is perpendicular to the direction of propagation of the wave, and magnetic field also perpendicular to the wave vector k, which essentially gives the nature of our electromagnetic waves and gives us idea how the electromagnetic waves propagates. Basically using Maxwell equation we define an electromagnetic waves, and we have discussed in details those things. After Maxwell equations we studied the Ampere's law, right? Ampere's circuital law we studied. After that, from Ampere's circuital law, after that we studied also Maxwell Ampere's law. Let me write that as well. Maxwell Ampere's law. Okay. Then we discuss displacement current. Right? Displacement current we studied. After that we discuss Maxwell equations again, but obviously the integral forms, right? The integral forms. Okay, there are four Maxwell's equations. First one is for Gauss law for electric field, then Gauss law for magnetic field, Faraday's law, and the Maxwell Ampere's law. Four Maxwell equations are there. We know these things as well. Okay, after that we after discussing the Maxwell equation we also studied the we also studied the definition of electromagnetic waves. We can say that also the characteristics of electromagnetic wave. The major output was that C equals to root over mu naught epsilon naught. Even we can write it like this, right? These things we have already discussed. At the last of the class I will give some formula chart from which we can look at the all formulas regarding this topic at once. Okay, so and then we discuss the energy density, right? After that also we have discussed intensity of electromagnetic waves. These things we have already discussed in last four lectures. Now in this lecture I will discuss the spectrum of electromagnetic waves. Okay, so let me start today's lecture, which is spectrum of electromagnetic wave, right? So electromagnetic waves is basically the propagation of electric field and magnetic field, where the electric and magnetic field both are perpendicular to each other and also perpendicular to wave vector. We know that. We have also drawn the wave picture of electromagnetic radiation several times. We know that how it looks like actually, but there are some important characteristic for each wave. That may be our mechanical wave, that may be our any sound wave, or maybe electromagnetic wave, anything it may be, but for any wave there are some properties. Okay, we know these things already. What are those properties? Like the frequency, right? What is frequency is denoted by nu generally. These are the general notation which are used basically. Frequency, wavelength, these are very basic things, but still let me discuss, which is denoted by lambda. Velocity, which is generally denoted by v, but for electromagnetic waves it is equals to speed of light. That's why we have written, we generally use the notation c, stand for the velocity of electromagnetic waves. Okay. So, and we know that the relation between these things, also there are some other things like the wave number, which is denoted by nu bar. Then one important time period, time which is denoted by t. After that wave vector, which is denoted by k. These things are very important, right? So, and there are some relations between these parameters like nu lambda is equal to c. Okay. Also nu bar means the wave number basically, so it's essentially 1 by lambda. Okay. Again the time period we can define like 1 by nu. So these are the things. What are the definition of these things? Let me start with the frequency. Let me draw first wave. This is just an wave, not an electromagnetic wave. We are considering any mechanical wave, it may be, not necessarily the electromagnetic waves. This is a wave, right? So if this is a wave, then what is another one more thing, there is some amplitude which is generally denoted by a. These are the important things. This, now let me define, this is the amplitude for any wave, this is a amplitude. There are some formal definition of these things. I am not get into that because we are very much familiar with these terms. Just I am revising these terms. Amplitude, this is the amplitude which essentially signify the deviation of the wave for any particular instant from the equilibrium position. That's the amplitude. Okay. Now if we look in the frequency, before frequency, what is the wavelength? Wavelength means if we consider a full wave means from here to here. In these for these 2 points, the phase of the wave is same. Okay, so we can say that if any wave travels from, let's say, O to O prime, then we can say that that is a full wave. Full wave means they have traveled up full wavelength. That's why it is called the O and O prime is called full wavelength. After that it will be again repeated, because any wave propagates periodically. Okay, after again O prime it will make the same periodical propagation. That's why this O and O prime is called full wavelength. Okay, and similarly if we consider this point, let's say x, then OX will be half wavelength. Okay, so this O prime is actually lambda, full wavelength. Now what is the frequency? Frequency stands for the number of full wave for a unit time, that means in 1 second if there is a 10 full waves generated, that means the frequency is 10. We can understand like this. Let us say one fan, any fan, ceiling fan is rotating. Okay, let us say if a ceiling fan rotates 10 times per second, that means the frequency of that fan, rotation of this fan, we can say that that is 10, because that is rotating 10 times per second. Any frequency is a general term which stands for the repetition of any quantity which in a particular unit time. Okay, that may be anything, that may be full wave, that may be anything like that, as I mentioned, that circular rotation of the fan, that may be any kind of parameters. But here for wave, the frequency stands for the repetition of the number of full wave in a unit second. Okay, so let us say in 1 second there is 10 full waves generated, that means in that case the nu will be 10. This is the frequency. Okay, so it is clear that in 1 second if new full waves generated, then a wave travels nu times lambda in 1 second, because one wave length, one full wave length is represented by the lambda. The length of the full wave is lambda. Now at a particular second, any 1 second, it generated 10 full waves. That means the length is 10 into lambda, that means nu into lambda. Here 10 is the frequency which is represented by the nu. So nu lambda is the distance covered by the any wave in 1 second. So that should be essentially the velocity of that wave, which is equals to c here. So that's why nu lambda is equal to c. Okay, and the time period means that time required for a complete oscillation, or we can say that for a time required for to generate a full wave. It is very easier to understand. Let us say nu is the frequency, right? That means we can say in 1 second there are new full waves are there. So one full waves requires 1 by nu second, and that is defined by our time period. So that's why t is equals to 1 by nu, right? And another one is nu bar. Nu bar is the wave number, that means the number of wave actually. So again we can write in one wave in lambda there are one wave, right? One wavelength. Okay, lambda distance, we can say lambda distance. There is only one wavelength, or we can say one wave is there. Now in unit distance, any unit distance, there should be 1 by lambda wave, and that is equals to nu bar. So that's why we can write nu bar is equal to 1 by lambda wave number. Okay, so these are the relations. So we can classify our electromagnetic waves both in terms of frequency and the wavelength. Okay, we are considering here the electromagnetic waves travels in vacuum, obviously free space, because we have already discussed that if there is some medium, not the free space, if there is any medium, then what will happen? In medium the frequency only remain constant. If let us say there is some electromagnetic wave of frequency nu in free space, and from free space it enters in a medium, that may be in liquid medium, gaseous medium, any medium. So what happens, that nu remains constant, nu will be invariant over changing the medium, but what happens, the frequency is constant but the wavelength will change, and if the wavelength changes, then what happens, we know that c is equal to nu lambda. That means nu lambda stands for the velocity. If lambda changes, then velocity will also change. If we change the medium, we have discussed these things as well before. So that's why it's actually we should classify in terms of frequency, but we are considering vacuum, that's why we can classify in both frequency or the wavelength, because in free space or vacuum this relation always holds. So essentially if we can classify our spectrum in terms of nu or lambda, it means the same things because it is interchangeable easily, as C is a constant term 3 into 10 to the power 8 meter per second. So that's why you can interchange very easily. Okay. So let me write down the spectrum of the electromagnetic waves. As in very first class I have written down that, but let me start again, and I will discuss this each of the part of the spectrum, each of the electromagnetic waves in detail in this class. Okay. So in this direction, let us say nu increasing, and in reverse direction, okay, lambda is increasing. Now if we make the order, then it will start with the radio, after that microwave, after that IR or infrared, then visible light. Actually we can only feel this part of the electromagnetic wave, the visible region. Other part of the electromagnetic waves our biological eye can't detect, can't sense that. Okay, that's why it's called the visible light. After that UV means ultraviolet, then X-ray, then gamma ray, and at last cosmic ray. So we can readily understand that radio wave has the largest wavelength and the least frequency, whereas the cosmic ray has the highest frequency and the least wavelength. So again we should remind one of the most important relation we have studied in our photoelectric effect, which is E equals to h nu. Okay, for any wave, where E stand for the energy of one quanta, right? Nu is the Planck's constant, h is the Planck constant, and nu is the frequency. So it is essentially clear that E is proportional to nu. So if nu increases, that means the energy of that quanta of that electromagnetic waves also be increased. That's why cosmic ray has the highest energy and radio wave basically has the least energy. So here we also can write Hc by lambda. These things are equivalent to each other. So this is our electromagnetic spectrum. Okay, so let me start with radio wave. Okay, what is the range? First we have to define the range for the radio waves. So wavelength, it is 10 to the power 4 meter to 0.1 meter. We are following the wavelength in meter unit, the SI unit basically. Okay, so we can also write in terms of frequency as well, because easily we can convert lambda to nu by just using this relation as we have discussed. Okay, this is the wavelength for any radio wave. What is the source of the electromagnetic wave for the radio wave? That is accelerated charged particle moving through a conductor or electronic devices like LC oscillator. That is a source. Okay. And the uses, that is very important. Before uses, detection of radio wave. We can detect radio wave by receivers aerials. Okay. And uses of the electromagnetic wave is very, we know that from the name radio, so it is basically used in radio, mobile phones, aviation, other communication devices. So these are the basic information for radio wave. Let me stop in this part. In next part I will discuss from the microwave and we will go through all parts. Thank you.